Oops, let me just stop. Okay, here's going. All right. Here we go. All right. All right. Hello, and everyone. Welcome to my dissertation. And we're going to talk about elongational polymeric flow exfoliation of graphite filler in a novel designed single screw batch mixer for continuous functionalization. All right. So this is done in 2018. All right. So to give you guys an overview, we try to this work is to investigate morphological changes under high shear extensional mixing involving both graphite and the polymer. And the aim is to try to find a way that it's simple to both modify, functionalize, as well as exfoliate graphene within a polymer composite, all done on the small nanoscale. Now, by trying to model the kinetics, mixing time, and concentration, we try to find ways to identify mechanisms that lead to the polymer deforming under this flow field, as well as how that affects bonding that's created at the interface. Now, we're going to first start with introducing you to graphene and then some of the gaps in industry which we're trying to approach. Then we're going to go to exfoliating graphite to graphene. Next, we're going to talk about the interfacial phenomenon that's occurring between the two systems. And then lastly, we're going to approach the polymer deforming under elongational flow. And here's a nice picture of graphene, which then I'll explain in the next slide. Now, to envision, graphene is if you look at this picture, is a two-dimensional, atomically thin sheet of material. And it's composed of many layer of graphite, as you can see in 3D. And it's an allotrope of carbon. So it has the same element, but arranged in different structures. And so if you were to take a sheet of graphene, you sort of ball it up, it becomes like fullerene, or you roll it up like a scroll, it becomes carbon nanotubes. Or if it's stacked and it's covalently linked, it becomes something like diamond. And it's been known to have great mechanical, electrical, and thermal properties, which you can find a lot of applications toward these areas, whether it be aerospace or commercial applications, or for structural materials and what have you. Now, the problem is that graphene is extremely expensive. To make a controversial statement, is actually it's about more expensive than any other commodity material, like on par with cocaine and and other like expensive things that are just on the market that's sold either legal or illegal. And it's also time consuming to make. So you have, it has a lot of harmful byproducts like sulfuric acid or nitric acid that you have to eventually try to get rid of when you try to produce this at a high yield. And the second thing is that trying to translate graphene to actual fundamental applications is a problem that's still trying to be overcome. What we are trying to do is we're going to try to take this two-dimensional material at a low dimensionality and put it into a high dimensional material using by compositing it within a polymer matrix. So that's sort of the approach we try to use. For adaptation of graphene, most likely you want to go down this slope towards scalability. Obviously, we know that people can produce expensive graphene at high yield and high quality using the Scotch tape method, but it's expensive. So it doesn't, that's not very useful. And so adaptation is direct towards scalability. And the next is, how do we interpret what is graphene? The American equivalent to a graphene association, as well as the European equivalent, given as a National Graphene Association and graphene's flagship, dictates graphene to be something about 7 nanometers, which is about like 20 layers or so. But we're going to take this as something that is traditionally graphite, and is in converting to graphene, there is a change in their properties given by the way in which it's characterized through the instrumentation that we use. And so that's how we're going to interpret what graphene is in this work. Now, the question that was posed in this thesis is, we're going to using non-conventional mixing, like what is the nature of the composite that's created, right? Like the type of bonding that's created between the matrix components, and if there is any property change that's resulting from that. And the next is under this type of mixing environment, like what deformations occur individually, either between the polymer as under elongational flow, or the mechanisms that lead to converting graphite to graphene. Now, we talked about scalability and looking at that previous slide where we're going to go down that slope. And for scalability, we look at industrial processes. And here you have an example of a large high-capacity extruder. And below is an example of of one of the first iterations of the batch mixer that we use in this work. And so the idea is that we're using industrial processes of mixing molten polymer and a filler material under a high shear environment. So the idea is that this process is economically beneficial because we lacked a secondary phase to aid in the mixing of this, so it produces no byproducts. And that we're focusing more on integration. So we're utilizing the polymer at the end of it. So if we want to make a nylon composite, we start with nylon and flake graphite. Or if we want to use a high melt temperature polymer, we're going to start with PEEK in our flake graphite and to use that to get to a final form. Now, the drawback in using scalable processes with graphene is that using conventional mixing, starting with graphene, hasn't really led to any a competitive composite where it's easily adaptable and say, everyone, I want that. And one of the issues is that graphene is really fluffy when you try to process it a lot. So it's a low bulk density. So there's a lot of environmental aids, inhalation issues, kind of dealing with like carbon black, but with much far better properties. And you have to sort of overcome that, as well as trying to overcome like filling issues, that especially if you want to put a high weight percentage in a final composite. And so starting with graphite, we actually can overcome this issue. Now, the objectives that we're going to try to talk about is we're going to try to detect the type of bonding that's created in a graphene reinforced composite. And then next, we're going to try to find the conditions where the deformation is occurring and like the type of bonding that's affected by it. And then next, like we're going to try to identify mechanisms converting graphite to graphene continuously. So you get an idea that what we're going to do from here on out. Now, there are some limitations. We're using engineering grade polymer, so it has a very defined molecular weight. So we're not using some niche biopolymer that's in dilute concentrations. Next, and it's also stable. Next, we're using it's all done under laminar flow, so no chaotic mixing. And the last is, as I mentioned before, this is not done under dilute conditions, and so the matrix is assumed highly concentrated or homogeneous. Now we're going to start talking about graphite being converted to graphene. And here's this picture of a mechanical exfoliation of graphite in a pencil, and it's sort of going across a piece of paper, which will lightly start to approach. And we're going to go to the literature review. All right. Now, to look at what other people have done to try to exfoliate graphite to graphene, here we have an example of a piston-driven method where you have molten polymer coming to the inlet, and the piston drives material back and forth, shuttling it in between this small orifice. And in this small orifice, the idea is to cause extensional mixing, right? And so you can see that as we look at the strain map here, and you can see that regions in red are where extensional mixing is occurring. And it's only occurring at a very small fraction of the volume within that mixing region. Now, what you want for efficient mixing is you want the materials to undergo the same time, temperature, and shear history. And so here there are areas where it's under compression and it's under no mixing at all. So that's not an efficient way of mixing when you're trying to produce a lot of material and trying to hopefully try to exfoliate in a very short amount of time. All right. Another method that people have used to try to exfoliate graphite to graphene is if you imagine you have a large extruder and you pump in CO2, starting with graphene and your molten polymer, those CO2 forms bubbles, and those bubbles want to try to expand. And so in between the expansion of those two bubbles, you have your like little micro elongational mixers. And this would cause separation of the flakes and hopefully try to make exfoliation efficient throughout the volume through that bubble expansion. But
Excuse me, just I think it's better for everybody to mute
yeah,
my bottom
might be
part.
a little bit easier because it's a lot of,
We don't hear your sound.
okay. All right, everyone's good? Thumbs up? All right, cool. All right. So for bubble expansion, so when you imagine, so you all these have these micro, extensional mixers. Now, the drawback through experience that we found is, when you add in a secondary mixing aid that creates bubbles in the extrusion process, then you got to get rid of the bubbles. And that is not always, that's a whole cumbersome process to deal with. And so you have this secondary component that adds in another complex step once you get to your final composite. So the idea is we want to reduce complexity in our final material, especially in the processing and processing. Now we're going to talk about our work, and this is a paper that was produced about 2 years ago, and it's touching on the three first patents that we got in this in exfoliating graphite to graphene. And here we start with a nylon, which is PA66, and graphite. And these are exfoliated continuously in an extreme screw mixer. And this is done without an additional mixing aid. So you have the polymer and the flake graphite and your novel mixing environment to create graphene in situ. And so we're going to talk about this paper and some of the results of that. Now I'm going to talk about the experimental work. Now, to get us in the mindset of what makes this unique, we got to look at the difference between shear flow versus elongation flow. Now, in looking at shear flow, imagine you have a fluid and you sort of take a needle and you take a syringe and you make a small droplet into the volume of the fluid, and it has a different viscosity, so it's able to suspend in that fluid. Now you have two plates, and one plate goes one direction, another plate goes another direction, creating shear flow. It deforms up into a particular limit. And here that maximum deformation is about 40, should be 45 degrees, but I think it looks about 30. Now, if we were to do that same thing under extensional flow, you see that there is deformation leads to sort of elongation. Then eventually it sort of stretches like a rubber band. And once that rubber band reaches its limit, it breaks. And so when that break happens, you create these new surfaces, which then will show in the later slide that those small little droplets could then be also elongated, stretched out and broken and onto continuum. So here's some work that was actually done by Taylor, which helped us interpret some of the work that's done in the paper. Here you have a plot of the critical capillary number, which is the number that's used to create a new surface or exfoliate once you exceed it, versus the kinematic viscosity. And this is being the viscosity between the dispersive phase and the continuous phase. Now, the dispersive phase is your exfoliate. And as you increase higher concentrations of your exfoliate, you move from left to right in this curve, your critical capillary number is still pretty low. So the energy that requires to create new surfaces is still low, even in, let's say, a molten polymer, or if you were to have in a fluid in a liquid system. So keeping that in mind, you see how efficient extensional mixing is, so as to cause deformation at even such a small level. And I think we'll show that in the results from here on out. Also, for simple shear, you see that maximum, there's a limit to which you can actually exfoliate where the critical capillary number just jacks up increasingly high, which means that for conventional mixing, it's not efficient. Now, how we calculate exfoliation is that we first started with X-ray diffraction. Here, graphite, if you imagine as a deck of cards, has a thickness, and that decacard thickness is considered the graphite sort of C-axis, and it's indicated in your diffraction profile as a 002 plane. So if you look in the literature, everyone's going to talk and look at this 002 plane saying that you're exfoliating. And by taking the characteristic of that peak, which being the full width at half max, what you can see here is that they have maximum intensity in the width of this. You can try using Shearer's equation, you can calculate the crystalline thickness of that material, and you can figure out the degree of which you're exfoliating. Now, in looking at that analysis, one of the things that we did is that we did by calculating the crystalline thickness as a results to time, we see that from 10 minutes to 45 minutes, we got about a 76% reduction in crystalline thickness. And we're actually able to exfoliate and generate an approximate size all the way down to about 14 or so nanometers. Now, one of the caveats to talk about, in which we sort of went back and forth, is like, how much graphene do we have in it, right? And actually, we'll see that we actually have a lot of graphene that's actually below that 14 nanometer mark. And that 14 nanometers is more of like an approximation, right? And so graphene being very, very small will ultimately be ate up by the background of the X-ray. And we'll kind of see examples of this using interfacial characterization methods that, that we actually have a plurality of graphene flakes in there. And this is as I said, this is a general approximation. Now, in fitting the data of exfoliation, one of the things that we found is that it fits a parabolic, it has a parabolic fit, and that this parabolic fit is interpreted as driven by diffusion. So if you imagine the PA66 polymer sort of diffusing in between layers of the graphite galleries, aiding as a mechanism to exfoliation. And now there are other mechanisms that actually reduce the size of graphite that we'll see, which we'll talk about a little bit later. Now, another thing that we found out is that PA66 is semicrystalline, so it should produce a diffraction pattern. And so we actually end up seeing that, where we have the first being for PA66 being 100, and the second being 010. And these correspond to the hydrogen bond direction for the first one. And the second one corresponds to the intra-sheet thickness for the second one. And we observe that they're changing as we exfoliate over a period of time. And so we're trying to figure out what that change is, and if that would affect the type of, if we get the changes that were actually occurring within the matrix given by the polymer. And we'll sort of touch on that here. Now, one of the things that we did is we took that crystalline thickness for the one direction, which is the 100, the hydrogen bond direction, over the intra-sheet direction, and we plotted and looking at the sort of anisotropy of that domain, of those domains. And what we found is that with the addition of graphite, or converted to graphene, that the maximum hydrogen bonding characteristic is 10 minutes, is higher, 10 minutes longer than the ones without graphene. And one of the reasons why we believe is that since PA66 has this sort of characteristic, that a loss in that hydrogen bonding characteristic is a pretense to the onset of degradation. And so the addition of exfoliating graphite leading to graphene actually creates, sustains the matrix and actually prevents or slows down the onset of degradation, and that it also produces these sort of anisotropic domains given by the type of flow regime. So that's something that's interesting, and also that's stated that graphene does have this sort of characteristic in trying to prevent oxidation, right? Or at least slow down the onset of degradation. Another thing, and we're trying to look at the morphology, we actually found that when we take an extrudate and we notch it and we put it into cryogenic temperatures and we fracture it, we start to look at the top surface to try to observe some of the features that are on there. And this helps us to identify the degree in which it is exfoliating, so we don't see any large flakes of graphite, and also the type of way in which it's locked in within the surface. And so one of the things that we found is that we believe exfoliation is caused through where you have the polymers on the top edge, where you have this sort of a hole left, and you can see there are regions where there's hole is generated, and then there's a key conformation where there's a key sort of locked in, where the polymer is either on the outside edge as well as the a turn like other edge, sort of causing the deck of cards to go in either direction. And we'll see examples of that in the later slides, which is one of the reasons why the voids are created. Now, we talked about how the polymer is adhering to the edge of the exfoliated graphene sheets. And we can see that where you have this sort of edge-on adhesion in another polymer system that's also a semicrystalline polymer, and see how it adheres really well. And we believe one of the reasons this is caused by is we're causing these sort of dangling bonds. So we're ripping the sheets on the edge, causing moments where high potential energy is created, and those dangling bonds want to be satisfied. You see they're satisfied by either folding over, or either satisfied by bonding with the polymer. We believe that that's one of the reasons why we would get this sort of features in the surface morphology. Another thing, we talk about how it's bonding to the surface, the polymer bonding to the surface of the exfoliated graphene, is that you can see it's sort of, as the polymers here is laying down and sort of stretched and elongated, and the graphene that's being created is actually having a very close and intimate contact with the surface through the same process. Another thing that we found is that for most processes, you want to retain a high quality graphene sheets. And so here's an example where you have a large area graphene sheet that's created through exfoliation. And it's so large, it's sort of really draping over the surface of the fracture surface. And it has these sort of substrate effects where, as it's laying on the surface of polymer, it has these sort of wave-like structure that's generated. And that's something that's clues to some future work that I'm actually thinking about on some of the substrate effects where you have graphene laying on a polymer surface, and some of the interchanging things that is occurring, which are very, very interesting to study. But we can actually retain high quality sheets due to our sort of industrial related process. Now, we talk about taking sheets of graphene and how they're ripping at the edge, right? Due to the creation of dangling bonds. And so we see an example when we're trying to make our TEM samples that it creates these folds right here. And these folds are created by these bonds to be satisfied by something, and they're satisfied by the graphene sheet by folding over. And we'll see an actual example of that. And we see how thin this is given by, we can make out the steps, we can make out how transparent it is under electron microscope. So this is good that we actually have graphene that we can visually see, and that is other treatments that relate to mechanisms leading to the size reduction of graphite to graphene. Now, we talked about if we're getting graphene or not, right? Is it smaller than the X-ray data that shows? And we see that we actually have 10 layers and 7 layer edges, and so 10 layers being many layer graphene, and if you're less than 5, it's few layer graphene. So we have a composite that has a concentration of few layer graphene, and that we talked about how the dangling bonds created this sort of ripping, and that ripping has to be satisfied by something, by either curling over. And we can see, as it's really thin, that curl is actually happening at the angstrom level, where this is actually acts as a clue to the type of things that are going on in our exfoliation process. So, all right, now when we talk about the degree of disruption that's happening in between the layers, if it's going on at the nanoscale. Now, this is a good example where we're actually causing planar disruption, right? So this is converting from a traditional AB stacking of graphite to an ABC stacking, which we cause the planes to literally just rotate. You can see that there's a rotation when we look at the point diffraction, and this is at a really thin sheet of graphene. And so we're causing disruption all the way down to that fine level, where that Taylor's plot says that we can still exfoliate, we can still cause disruption even as the surface gets smaller and smaller and smaller. So that actually, that proves some of Taylor's work, that it can be done in a molten polymer system with graphite going to graphene. And you can see that for the highly crystalline graphite, you have the sort of six-membered rings due to the point diffraction given by these sort of moire fringes. Now, to take a step back and sort of really get an idea of what this is, we see that this elongational flow in the molten phase, it led to sort of large area nanographite and multi-layer graphene. And we looked at it from, we can confirm it through the X-ray diffraction and electron microscopy. We found the mechanism of being, one of the mechanisms for exfoliation being diffusion driven, converting graphite to graphene. And also that there is a diffusion also led to sort of that erosion or friction on the outsides, causing free radicalization or dangling bonds that are created, taking part in the size reduction process, causing the edges to fold over. And next one, we've actually found that the polymer actually undergoes a very unique microstructure, that I have crystalline grains that are anisotropic. And the next, we're going to actually talk about the interfacial effects that happen in the process, which is, I think, the second paper that we did. So here we go. We talk about the interfacial phenomenon, and we look at an allotrope of carbon, where you see some of the bonding characteristics that would typically happen on a graphene sheet. This is CNT, but the structure is the same, so the type of bonding would ultimately be the same. There's literature review. Now, covalent functionalization of graphene, we look at what we'd actually expect from the Raman work. And we see that, look from Raman spectroscopy, and we see that if we take a sheet of graphene, it has this sort of G peak. And the G peak in the Raman spectroscopy corresponds to sort of the in-plane vibrational mode. So if you have a sheet of graphene, you're going to have that has minimal or almost no defects. It's going to have a high G peak vibrating on the surface. Now, if you were to functionalize it, or rehybridizing, converting that sp2 carbon to sp3, in this case, through free radical functionalization, you're going to cause the appearance of this D peak. And so this D peak is indicative that you're sort of functionalizing the surface or the edge of a graphene sheet. And so you sort of modify sort of the pi-pi conjugation. And so we believe that the routes for functionalization is either due to free radical functionalization or a route leading to electron donating. Now, we look at the results as relate to non-covalent versus covalent functionalization in regards to mechanical properties that are created. And here you have graphene that's functionalized with methyl methacrylate, and they put it into a polyvinylidene fluoride matrix. If you look at for non-covalent functionalization, the actual break stress is around about 45 megapascals, which also has a low modulus given by the percent strain at break being around like 15%. But when we look at covalent functionalization, we see that the break stress is about 100 megapascals, and the break stress is about less than 5%. So it's high modulus and high break stress. So the addition due to functionalization actually leads to an improvement in mechanical properties. So this actually acts as a clues that we have that it's covalently functionalized. Graphene has an improvement in properties. Now we're going to talk about the second paper that we did as it relates to functionalizing led to mixing graphene in an elongational flow regime. Here we take the PA66 and the graphene system, and they're mixed together. And we actually found in this paper, we found that they create primary bonds. So they're covalently bonded to each other. And that these primary bonds show evidence that there is a preferential chemical functionalization on the edge, on certain specific edges of graphene. And so we'll end up seeing that. And so we're going to go to the experimental work. Now, we're going to do four instruments we're going to use to characterize, four techniques we're going to use to characterize this. Mechanical properties are going to be done. Transmission electron microscopy, which we've seen images of before in the previous slides. X-ray photoelectron spectroscopy, which we're going to use to look at the top surface of the material, so the first 10 nanometers or so. And a Raman spectroscopy, which we're going to use to get an idea of the hybridization and some of the characteristics of the graphene that's generated. Now, Now we look at the covalent functionalization using XPS. We see that if you have a binding energy shift to the increase, you actually get oxidation, right? And so if you get a binding energy, you can see by this arrow here, if you have a binding energy shift that's going to the decrease, you get reduction. Now, in looking at nitrogen, because most of these systems both have carbon and oxygen, nitrogen actually aids into having a good resolution of the system, so we can actually see the changes that are going on. We see that there's an oxidation of the nitrogen in the amide group of the PA66. And so that tells us that we're getting primary bonding to the backbone of the polymer. Now, and it exists for the mixing at 20 minutes. Now, when we look at it as regards to, as we increase the mixing from 20 minutes to 30 minutes to 45 minutes, we see that we're getting a bonding energy reduction, right? And so when we talk about some of the X-ray work of the polymer sort of losing that hydrogen bonding characteristic, we see that binding, that this also acts as clues that there's a possibility of the onset of degradation due to the extendedly long time of mixing. And so you can see that for the 45 minutes, and the 30 minutes is slightly retained, where that reduction is going on. And so this actually supports some of the crystalline anisotropic characteristics that we got in the previous section. Now, the next thing we're going to talk about is Raman spectroscopy. And we see that we have three peaks that are characteristic of graphene. Now, the first thing we're going to talk about is our D peak. And if you remember from the literature review, is that the onset of the D peak says that we're actually getting bonding or rehybridization going from the sp2 to sp3. And you can see with the starting graphite that as that D peak is slowly increasing, and it jumps up from 20 minutes and then 30 minutes and then 45 minutes. So this actually acts as a clue that we're actually modifying the graphite to graphene, causing sort of dangling bonds to being created. And the XPS reveals that they're primary bonds. The next thing that we're going to look at is a G peak. So that's sort of that in-plane vibrational mode. And there's a shift in the G as you go beyond 20 minutes. We believe that shift is that since we're creating these sort of small, really thin graphene sheets, they're much more compliant, right? So they're very flexible and they're very sensitive to substrate effects. So given that the combination of the flow is extensional flow, extensional mixing, as well as they're being so flexible, that's one of the reasons why we get this sort of a red shift, right? Because they're under tension. Right. And they want to conform to their substrate. So that's an indication that we have graphene that's also flexible, but also has very intimate contact that makes us clues to the to secondary bonding. Now, the other thing that we're going to lastly talk about for Raman is our 2D peak. And the one thing that you want to take here is that you have the 2D1 and 2D2. And for graphite, you have that big 2D peak. You can see that it sort of shifts and broadens as mixing time increases. Now, when you have multi-layer graphene, you create these modes, or these phonon modes actually split into 4 modes. And so, and as leading to that 2D sort of slowly start to increase. And so that splitting of those four modes says that we're getting a plurality of graphene within the surface given by the Raman work. So it actually speaks to the fact that we have many layer and also few layer graphene within the material. So this is another clue that's seen from the TEM results. Now, we talked about edge functionality due to selectivity, and we want to see, and we look at the move this out of the way. So we look at the top layer in the top right, and we see that there is it's nice smooth edges. And we notice that if we look at that edge and we rotate it by about 60 degrees, we notice that this sort of looks very jagged and rough. And so that actually got me thinking, okay, like, what does this mean? I mean, it's 60 degrees and, graphene is hexagonal. Like, it should tell us something about the structure. And so in doing a nice literature review and really taking a step back that I thought about in this paper, is that we know that graphene has different edge structures, one being armchair and the other being zigzag. And if you can see the sort of example of what the edges look like, You can see that if we were to take that same surface of graphene and sort of translate it here, we can see that along this edge will be very, very close to our zigzag arrangement. And so this actually speaks to act as clues is that there are selective edges that are sensitive to functionalization due to the energy on the edge of that material, right? And so this actually acts as a clue that there are the graphene, even though we exfoliate it within the polymer, that there are edges that are sensitive to functionalization, and also sensitive to erosion, leading to bonding or creating of these dangling bonds, in which we saw by the folding of the edge in the previous slides in electron microscopy. So we thought that was actually very interesting. I think that the paper speaks a little bit more on. The other thing that we found is that we talk about sort of primary bonds being created as well as secondary bonding happening. And given that our polymer is semicrystalline, we also should be able to find evidence of the polymer in the TM results, and in some evidence. And one of the things that we found is sort of this shadowing effect that occurs on the surface of the graphene. We can see that it's graphene given by how the structure is sort of arranged in a sort of oriented array. And we believe that this is a secondary bond that are created where you have a flat sheet of graphene and the polymer is actually laying on top of it. And it's having sort of this intimate contact with the graphene sheet. And we sort of talked about it in the Raman work also, where it's sort of under tension. And I believe that that's this, as well as the TEM microscopy results, that provides clues that something like this is going on, where it's also, I think I'm going to talk about where it should be studied more about how this sort of thing kind of occurs, and what type of electronic properties it would actually have, will be sort of interesting to expound upon. Now, the next thing we're going to talk about is when we look at and looking at the surface very closely, we actually end up seeing that there is this sort of arrayed structure, which doesn't necessarily correspond to something that's traditionally graphene or graphite. And when trying to calculate it, we found that it's about 2.13 angstroms in size. And in looking at that, it doesn't, we're trying to figure out, okay, what does it actually correspond to? And looking at the point diffraction of it, we see that if you try to arrange these together and kind of calculate it, it still doesn't relate. So we sort of took a step back and tried to understand, okay, what does that actually mean? And in looking at it, one of the things I found is that if you were to take an AB stacked sheet of graphene, bilayer or trilayer graphene, and you were to shift it to the right, you get this arrayed pattern. And so this actually speaks to the fact that we know that we can rotate the sheets from AB stacking completely, but the fact that we could shift them even just a little bit, there's ability for us to possibly control the degree of rotation. And so, since I know in the literature, everyone's talking about the exotic properties of graphene, where as you rotate graphene, you get these interesting properties that could be translated to optical or other type of electronic. This is actually speaks to the fact that our process could actually generate a high concentration of graphene that could possibly have some exotic properties due to sort of tailoring the type of shift that we get. So we thought this was actually interesting to speak on the type of deformation that is occurring in our process all the way down to that angstrom level. Now, lastly, we're going to talk about the mechanical properties, which I think everyone came here to see. Is that, and when we actually see a polymer that's placed into the experimental method in the same instrument, that due to the addition of graphene, we see that we get an increase in our break stress, going from PA66 that's done at the same time, from 55 megapascals to around 61, as well as we get a massive increase in our modulus, going from 2.4 to 13.06. So it's about almost a 600% increase in modulus. So that's, this actually provides clues that, the polymer has an intimate contact with the graphene that's created, as well as the fact that we have a good stress transfer between the material. And that if we recall from the work that's done in a literature review, is that this speaks to the type of covalent bonding that we're forming, leading to our increase in our mechanical properties. And also one thing to speak is that, so this is values for a pristine, perfectly produced PA66. And now the values are going to be high like this because this is processed at a much lower time, and this is under ideal industrial conditions, which makes sense for having something like this, comparing these two, since these are under experimental conditions. So when you look at that data, you should have, and when you look at the results and compare them, you want to translate it to that. But one of the things that speaks more to is the fact that our increase in modulus, which is the indicative, because polymers are ultimately flexible, and you want to make them, for engineering applications, they should be stiff. Now, lastly, take a step back. We see that in our process that we have multi-layered graphene that's formed, and they're chemically bonded to the matrix, or primarily bonded to the matrix given by the oxidation of the nitrogen in the amide group. And also this primary bonds as well as the secondary bonds led to an increase in both the strength and stiffness of the composite. And then also we can see that through the Raman and TEM also speaks to some of the secondary bonding characteristic given by how the G peak is sort of strained, as well as how we see that the polymer has a very close and intimate contact with the surface given from the TEM results. Next, we'll actually see that on the edges that are susceptible to erosion or dangling bond creation, we can see that it's possibly due to a zigzag edge on the graphene sheet, and that's where we believe that primary bonds are likely forming. And lastly, we're going to actually talk about the bonding that's suggested from the polymer. So if the polymer actually undergoes a change in potential energy, which would lead to the possibility of it actually bonding to the exfoliated graphene in situ. All right, so here's our last section we're going to talk about, and polymer deformation and elongational flow. And here you can see a sort of a polymer under sort of a random walk conformation, and then it's elongated and stretched, and it's under no entanglement. And here the same thing, and there's some small degree of entanglement given by this cartoon. Now, I'm going to talk about the literature review. Now, you recall what I talk about where you have simple shear versus elongational flow, and how the deformation is occurring where it deforms to a particular limit. And then for here, as a rubber band, it's sort of stretched out, it extends the rubber band out, and then eventually breaks once it exceeds a particular limit. And then that goes on to continuum. Now, let's look at it as it relates to a dilute system. And that's where this idea first came, where you look at biopolymers that are under an elongational flow cell. And this is fluorescently marked. So you have a biopolymer cell, and it's pulled apart under extensional flow. And as it's being pulled apart like a rubber band, you see that due to some of the surface characteristics, that it has it's either has a dumbbell kinked or half dumbbelled or folded as it's trying to pull itself apart. And this happens when that sort of hydrodynamic force exceeds that sort of elastic restorative force of the polymer wanting to pop back together. And one of the things that we're going to try to envision this is that we're going to try to think of it as an interconnected ball and spring arrangement that has some type of that has some type of length, right? And so these adjoining springs are going to be concepts going to be used to try to look at, okay, how would if there's going to be a change in potential energy of this of a polymer under these same conditions, what's actually going to happen? What does that actually mean? Now, we look at how things go in the dilute system. Now we need to actually look at it how it goes in a molten or highly concentrated system. And so we found this work that was done by Brown and Wool, where they looked at entanglement, right? And so you have a polymer that's under a highly anisotropic flow in a molten state. And what they found is that as these guys are pulled up, as the increase in anisotropic flow increases, this entanglement actually reduces, changes at the interface, and that change is actually a lower entanglement density. So imagine this is sort of kinked and cocked together, and as the flow goes in either direction, imagine if you throw our first picture where there's the arrangements are side by side, they're ultimately pretty much stacked together in a very, very low density. And so we're going to use that concept to see if we could take a molten polymer and sort of pull it apart and how that actually would affect in some of the results, and we'll see later. Now, I talked about that sort of ball and spring arrangement where you have these balls being sort of your elemental unit, and these springs being their, how the polymer chains are connected. Now, imagine that they're separated by some x, right? So it's unstrained, and so it has some type of displacement, and in between each spring, having a spring constant. If you were to stretch that out, there would be a change in your potential energy, right? Under some type of displacement. If you consider that change in potential energy and assume that that force is conserved, given down here, then you try to integrate that force, you realize that that's some work, that's being done on the system, right? And so if I have a fluid force that's coming down and it puts work on the polymer and it elongates out, then that elongation is my change in my potential energy. And so we're going to use that concept to try to interpret some of the things that the polymer undergo under extensional flow. Now here's the experimental work. Now this is done using Kissinger's equation. So Kissinger found a non-isothermal method, and so looking at some of the kinetic parameters for some of the reactions that go on between the polymer solid state being, and this is done by taking in this work 3 different heating rates at 10, 20, and 30 degrees Celsius per minute using differential scanning calorimetry. And the idea is to try to get an idea of the change in the activation energy. Get an idea of the activation energy from this process at these sort of equilibrium temperatures. And our temperatures are going to be the melting temperature, recrystallization temperature, and the glass transition temperature. Now, it starts by using the same mixer that we use, extensional mixer used previously. And this is done at their processing temperature. So it's 360 degrees Celsius for polysulfone, which is here, and 320 degrees Celsius for polyphenylene sulfide. It's allowed first under both high shear, which is LS, high shear, which is HS, and then low shear, which is LS. And then first allowed to go out and then drop into liquid nitrogen, sort of have a frozen state. And then next, with that same material, it's allowed to go and then drop onto a glass slide. So it's allowed to slowly cool down to room temperature. So the idea is you have 4 samples for each different polymer, both under high and low shear. And both under high and low shear, those ones that are cryogenically cooled as well as room temperature cooled. So we're going to kind of look at those different cases. Now, for the calorimetry results, to understand what differential scanning calorimetry does is that as we scan at these 3 different rates, we get 3 different equilibrium temperatures that we're going to look at. For polyphenylene sulfide, we're going to look at our glass transition temperature, which is below 100 degrees Celsius. The second is the recrystallization temperature, which is after between 100 and 150 degrees Celsius. And the last is beyond 250, which is our melting temperature for polyphenylene sulfide. So this is a semicrystalline polymer, so it has a melt state. The next is we're going to look at polysulfone. And polysulfone, being amorphous, just has a glass transition temperature, in which we see here. And we're going to characterize that to look at some of the changes that we normally would get. Now, this is something that I thought that was actually very interesting. One of the things that we found between the two and looking at the activation energy is we see that for the low shear, we actually get a higher activation energy compared to the high shear. And you look at the change in the activation energy, you see it's small between the difference. So imagine something that's fully extended and then relaxed. Now, for the high shear, because the change is smaller, like it's an extended rubber band that is only allowed to relax very little. But for the one that's under low shear, it's extended fully, and then it's allowed to relax all the way. So you get an idea that under low shear, it's not deforming the polymer that much, as well as the fact that because the activation energy is small, that the entanglement density is small, right? And so you have these, in order for glass transition to occur, you don't have these chains sort of bumping into each other, trying to spin or trying to mobilize as you're approaching the sort of the glass transition temperature, which is also one of the reasons why you get this sort of change in activation energy. Now, let's go to the next one, which I thought this is interesting, and this is actually going to translate further down, is that for the semi-crystalline polymer, the opposite effect happens. So you know that for the molten state, you have a reduced in entanglement density because the chains sort of arrange by themselves. But since our activation energy is higher, we think that two things are going on. Is that as they are oriented side by side, semi-crystalline polymers tend to be a little bit more flexible. And so we believe that flexibility actually changes sort of the radius of gyration, as well as if the radius of gyration is changing, they're getting closer together so that there's some type of steric hindrances that are going on. And so that actually attributes to an increase in activation energy, and which is one of the reasons why it's higher, because it's fully deformed. We interpret it as being slightly closer together. And when we look at that, the change as it's going down to room temperature cooled, because it's also flexible, there's a possibility if it wants to pop back a lot more faster, even though it's under the fully extended state. Now, if we look at that, how it relates to recrystallization, the change is still relatively small in regards to our activation energy, but the idea of it being sterically hindered and being closer together still translates. So, and if you look at the frozen in state, it has a slightly higher activation energy. And so that means that it's still intimately closely contact together. And as it's trying to recrystallize, it's trying to eat up that energy for recrystallization to happen. And it's much higher compared to, let's say, the cryogenically frozen, where it's not as highly deformed. You can see that's one of the reasons why the sign is negative, is because of that steric hindrances that are going on in that system. Now, when we look at melting, the same things still translate, right, to the flexibility and the fact that they're closer together, causing sort of hindrances, where you have the not as highly deformed state, where for this, polyphenylene sulfide is a polymer that wants to crystallize, right? And which is also one of the reasons why the activation energy is so high right here. And that the difference between these two makes sense because the frozen in state, but they're just also not closer together, and then sort of room temperaturely cooled, and they have like a higher degree of entanglement and things like that. It has enough time to have these crystals that it wants to form, which is one of the reasons why this difference is so high. But when you look at the difference between these two, that sort of steric hindrances are still playing a part in the type of crystals that are formed, which is one of the reasons why the change in activation energy is so small, as well as why as well as why these are still so relatively high, because those hindrances are still playing a part in the formation of these crystals upon melt. Now, to summarize this work, we started with dilute polymers to try to interpret this theory, and then also we tried to apply the molten polymer. And then, when looking at semicrystalline, what we actually found is that this creates a high potential energy for polyphenylene sulfide, sort of reducing the radius of gyration and trying to shorten that distance between adjacent chains, causing the sort of hindrances to occur. And so this sort of change in sort of the conformation, we believe it increases the chances for self-interaction. And cause due to this sort of highly anisotropic flow. Now, for the amorphous polymer thing, we found is that it led to sort of a reduction in entanglement, right? And so this leading to like a low activation energy, which the sort of the polyphenylene polysulfone is not interacting with itself, and so it's and you can see that as sort of as I mentioned, the glass transition temperature is still low. So we first started this by saying that the chain sort of approaching sort of one-dimensional surface or like a one-dimensional extended polymer. But what we actually found is that chain flexibility actually plays a really strong role on how these would interact and actually would cause bonding to occur. Now, to summarize, we took graphite exfoliation, we took interfacial functionalization, and we took polymer extension, and all used to try to create a graphene enhanced polymer matrix composite. And so all these things are going on in that system. Now, let's go back to the first question that we posed, is that, what is the nature of the composite through the sort of non-conventional melt mixing under pure elongational flow. So we see is that we developed a composite where you have primary and secondary bonds formed between the matrix and the exfoliated graphite leading to graphene. And also that the composite had these sort of morphological changes that occur within the graphene and in the creation of anisotropic crystals and the polymer, which led to sort of our increase in modulus, as also the increase in our in break stress as compared to a polymer that doesn't have it. Next, like under the same mixing, like what type of deformations occur like that make the resulting composite possible, right? What changes? So we see that the composites found that form a distribution of a pH66 in between the galleries of graphite, leading to one of the mechanisms for exfoliation, so causing sort of that planar separation, as well as resulted in sort of a preferential edge ripping, causing sort of the free radicalization, leading to bonding to occur, as well as how the elongation of the polymer itself has a sort of increase in our potential energy, and then how that flexibility and increased potential energy reduces a sort of that cross chain to chain distance, which possibly makes bonding possible. Now, to summarize, so that this process has potential converting plastic and graphite to a graphene reinforced polymer matrix composite, which is reproducible as well as done simply and scalable. This also produces large area graphene flakes, which we saw in that picture, which it's draping over the surface that form primary chemical bonds to the matrix, which has our increase in mechanical properties. So it's translatable. And lastly, that this is a condition where the polymer and the reinforcing agent both can contribute to the formation of chemical functionalization. And this is a case where we have mechanical work is literally creating chemical potential that leads bonding to occur. And some future work, so this will be done by taking catalytically modified, so I'm working on a project where this will be done by taking catalytically modified graphene using copper, nickel, cobalt, and we're going to run through the same process and try to study some of the interfacial characteristics of that system. The next thing that I'm still working on is trying to create a model of the interface and try to understand how graphene on top of a polymer, like what type of structural effects are actually occurring, sort of mimicking some of the things that we saw in our TEM results, as well as we saw in sort of the other electron microscopy images. And the next is we're trying to do some work where adding in other types of filler, whether it be 2D, 1D. Before also, we did some work we're adding through a 3D filler, whether it's a metal organic framework or covalent organic framework, and seeing the type of fundamental changes we get in that system. And lastly, which I'm still pushing on, is doing some STM work from Brookhaven, which should be interesting. Once COVID is sort of releases and makes everything a lot easier. Thank you, and questions.